Hey everyone, and welcome to your last video for Unit 2. And this video is about peroxisomal beta oxidation. So beta oxidation that is happening in your peroxisomes. Remember that peroxisomes are small organelles. We saw them as they related to hydrogen peroxide, a reactive oxygen species, hydrogen peroxide, and kind of neutralizing that by turning it into water and oxygen. Peroxisomes do that, but they also do beta oxidation, and this is the structure of the peroxisome. We have the lipid bilayer membrane around it, and then we have a crystalline core. It's not a lot to it. It's a very small cellular organelle, and not super complex. Also, because they are so small, we're not going to be doing a ton of beta oxidation there. Only about 10% of the total cellular beta oxidation is going to happen in the peroxisomes. The rest of it is done in the mitochondria, like we have seen before in our beta oxidation video. Now, if you were to be eating a high-fat diet, you start making more peroxisomes in your cells, and that shifts the relationship a bit more, the proportion, so that you end up doing proportionately more beta oxidation than 10%. So you start increasing the percentage of beta oxidation that you do in peroxisomes if you have more peroxisomes. Now, as for their function, over here we have a list of all the enzymes that we have in the peroxisomes and what they're going to be doing. I realize you cannot possibly see that. Well, maybe you can. But anyway, I wrote it out up here so that you can use this and follow along with the slide as we explain it. So our enzymes in the peroxisomes, and they'll go in the same order as the slide. So first, oxidase enzymes. The oxidases are responsible for oxidizing things. Things such as fatty acids, which is what we're talking about, but the fatty acid specific oxidase is acyl-CoA. Also within the peroxisomes, you have oxidases that are good for oxidizing other things like urea and uric acid. These are toxins that are byproducts of other metabolic processes. And over here in the picture, you have a toe with an accumulation of uric acid crystals between the metatarsal and the proximal phalanx here, so in a joint, which is where uric acid crystals tend to accumulate, and they cause pain. This happens particularly if you have a high-fat diet, and it's a condition called gout. You've probably heard of gout before. It's, due to inflammation, a lot of fat in your diet, a lot of sugar. Gout is often typically combated or can be lessened with curcumin, because that reduces inflammation and reduces uric acid formation, which lessens gout symptoms. So it sort of ties back to our antioxidants and all that. If you remember, curcumin was an antioxidant that is found in specifically turmeric, which is a nice spice for reducing inflammation. Anyway, I'm on a tangent again. Let's continue on with our enzymes. The next kind of enzyme would be synthetases, specifically for fatty acids, acyl-CoA synthetase. This helps to prepare the fatty acids for oxidation. The bifunctional enzyme, this includes anoyl-CoA hydratase and 1,3-hydroxyacyl-CoA dehydrogenase. The end result, oops, you can't see what I'm doing, anoyl-CoA hydratase and 1,3-hydroxyacyl-CoA dehydrogenase. What these are going to do are create NADH, so taking NAD and making NADH out of them. The fourth one are actually two. They're related. There's catalase. We'll do the second one first. Catalase makes fatty acyl-CoA. This might sound familiar to you from the beta oxidation video. When we broke fatty acyl-CoA into two parts, we get two acetyl-CoAs, right, and a carnitine. So beta ketothiolase is the enzyme within the peroxisome that breaks down the fatty acyl-CoA into acetyl-CoA. So we get the acetyl-CoA. Now, where is the acetyl-CoA going to go from the peroxisome? We'll think about that in a bit, because we don't have mitochondria on the peroxisome, obviously. It's not a mitochondrion at all. So we can't just do the Krebs cycle on it. So we need to think about where that acetyl-CoA is going to go. And then we have reductases. Reductases are good for oxidizing unsaturated fatty acids. And we'll talk about saturated versus unsaturated a little bit later. We already have mentioned that, but we'll mention that again. Okay, so our products from our peroxisomal beta oxidation, we're getting acetyl-CoA and fatty acyl-CoA, like we said on our previous slide. But where did these go? Nobody knows. They might go to the mitochondria, and then, acetyl-CoA could be used directly in the Krebs cycle. Fatty acyl-CoA could be turned into acetyl-CoA, and carnitine to be used for the carnitine shuttle. They might be hydrolyzed into acetate, okay, or they might be turned into acylcarnitine, again for the carnitine shuttle, which is involved in the mitochondria again. So nobody knows that yet. Maybe they will find that out soon at some point, but so far, don't know. Great, and then here's our saturated fats versus unsaturated fats. Remember we said it was all about how many double bonds of carbon we had, or how much hydrogen we had. The more saturated a fat is, the more hydrogen it has, which means less carbon double bonds. I drew a little picture in that previous video. This is a much better picture. See on here the saturated fat. There's one carbon with a double bond on it at the very end with oxygen. So there, just one. So one carbon double bond. And then all the other carbons just have lots of hydrogen. So they're a full complement of hydrogen. Each carbon can have 4 bonds, so all these carbons have as many hydrogens as they can, along with their carbon skeleton, their own carbon-carbon bonds. Now, an unsaturated fatty acid, there's one double bond, there's another double bond, so it has 2 double bonds on different carbons. That makes it unsaturated because it doesn't have the maximum amount of hydrogens. That double bond essentially kicks a hydrogen off of each of these carbons that are involved in the double bond. If we did that again, if we put another double bond, say there, then we would have another double, we would take the hydrogens off of those guys, and we would just have, even less hydrogen, and that would be polyunsaturated. So it all has to do with the amount of carbon double bonds and how many hydrogens, if we have the maximum hydrogen or something less because of those double bonds. Okay, so here's a picture of a polyunsaturated fatty acid. This one has a bunch. We have our one between it and between a carbon and oxygen. Then over here again, there's another one. Then all these carbon-carbon double bonds. This is just a really unsaturated fatty acid. So the more we have, the more unsaturated it becomes. Okay, so this is not, that's butter. So that's a saturated fatty acid. Okay, these are not healthy for you. Obviously, if you were to eat that stick of butter, that would be 1, gross, and 2, it would not be healthy for your body. These saturated fats tend to increase your low-density lipoprotein levels, which can clog your arteries, which is not good, obviously. Unsaturated fatty acids or unsaturated fats are good fats. So there's an avocado. You know how you always hear an avocado has good fat in it. It's a monounsaturated fatty or fat. So here, let me show you. That would be a monounsaturated fat, because it just, well, without the one I drew in there, but there, just the one extra double bond there. A polyunsaturated fat like sesame oil, that would be more like that. These are good. These tend to increase your HDL or high density lipoprotein levels, which are not going to clog your arteries because they're traveling in the venous circuit, where the LDLs are traveling in the arterial circuit. Also, the unsaturated fats are carrying extra fat out to your cells from your liver, while these are contributing to taking extra fat away from the cells and bringing them to the liver to be processed into other things. The saturated fats are solid at room temperature, so that's an easy way to know. The unsaturated ones tend to be liquid at room temperature, obviously not when they're in the form of an avocado, you know, or an olive, right? Or sesame seeds. But once you get the oil out, the fat, so you separate the fat part from all the other stuff that you have in these, you know, the avocado or in the sesame seeds or an olive or whatever one we're talking about, you get this oil and it is liquid. You know, it's like a cooking oil that you tend to use. Okay, and that is it. That is it for Unit 2.